All right, so today we are back to the little boxes. So just to remind you, for the whole week we've been discussing the operational approach to quantum theory. So we've broken things up into preparations, transformations, and measurements. And we had 3 postulates associated with that. Yesterday we talked about entanglement, and we were talking about the Schmidt decomposition, and I tried to give you an example of how you would do the Schmidt decomposition in practice. I picked a horrible example because it's not even a normalized state. If you actually write it out in the 0-1 basis, you can see that. So, well, this is now an orthogonal basis, and yeah, it's not even like a physical normalized state. So this morning I tried to come up with some examples that would work nicely and actually were physical, but everything was just numerically horrible, and I didn't think it would be very instructive to go through it on the board. So hopefully yesterday the process was clear, even if it didn't work out numerically. If it wasn't clear, I'm very happy to talk to you in the tutorial about it. I can show you on Mathematica how it would work. But unfortunately, I don't have a nice example that, that makes sense to do on the board. Okay, so let's go back to the postulates. Okay, so the first postulate that we saw was to do with preparations. And postulate says that a realistic preparation procedure is described by a positive semi-definite operator ρ with unit trace acting on the Hilbert space H. And so we already saw that there are 2 ways of building one of these general operators. So the first way was to create probabilistic mixtures of pure states. And so then the density operator describing that would be given by a convex sum of pure states weighted by the probabilities of preparing that state. And then the other way that we saw it is that we could create a pure state on an extended Hilbert space, so Hilbert space containing system A and system B, and then throw away system B and just describe system A. So the effective description of system A would then be a density operator. So let's just again look at a couple of examples. So again, I'm just going to focus on simple 2-level systems. So in the first example, if I, with probability P equals 1/2, I prepare the state 0. And with probability P equals 1/2, I prepare the state 1. Then, of course, the density operator is going to be the convex sum of 0 and 1 weighted by 1/2. Okay, and then in the second example, we prepare a maximally mixed state of system A and B, a maximally entangled state. And then we compute the reduced density operator. So if we want the operator for system A, we trace out system B. and we get an operator that looks like that. So we have some terminology to distinguish between these two types of preparations. Usually we refer to this first preparation as a proper mixture, and we refer to the second preparation as an improper mixture. I actually don't like that terminology. I would have swapped them the other way around, but maybe that says something about my philosophical leaning. But okay, so we have these two kind of, operationally, they're very different procedures. One of them is I'm preparing pure states probabilistically, and the other one, I'm preparing a pure state on a larger dimensional Hilbert space. There's no probabilistic uncertainty, but I just throw away one of the systems. And then I get two density operators that look exactly the same. I could just put labels on this if I wanted to, just to really emphasize that they're the same density operator. So if I have these two different preparation procedures, and in this case, I only have access to system A, is there any measurement that I can do to distinguish between these two preparation procedures? I see some heads moving. Yeah, so the answer is no. There's no measurement that you can do to distinguish between these procedures. So there's certainly no single shot measurement that you can do, but there's also no many shot measurement that you can do. Even if you prepare many copies of the same, if you go through the same preparation procedure many times and you do quantum state tomography, there's no way to distinguish between these two because they have the exactly same density matrix. And this holds in general. If you have two different preparation procedures that have this, well, if you have a proper mixture and an improper mixture, but both of them have exactly the same density matrix, then there's no way to distinguish between those. And I kind of find that a little bit troubling. And I think it's worth thinking about. Maybe you don't think about it now, but like over lunch, think about it a bit because it's, yeah, I think it's interesting. Yes, at one point, some of these lectures made it on Reddit, and in the comments, people were complaining like that the lecturers don't know how to use the boards, but it's really hard to figure it out. Okay, I don't want that. Okay, I don't have access to that board anymore. I think it's like it's possessed or something. Okay, so we've seen that if we have a pure state on a larger dimensional Hilbert space, we can reduce it to a density matrix, but can we go in the other direction? Let's say if I just write down some arbitrary density matrix. So can I start with some arbitrary density matrix on system A and then rewrite it as the reduced density operator of this composite system? And turns out that you can. This is known as a process called purification. So any density operator row A can be realized as the reduced state associated with a pure state on an extended Hilbert space, HAB, which is the tensor product of HA and HB. So things kind of get even more weird, because I can have this preparation procedure that's this probabilistic mixture, but then I can mathematically represent it as the reduced state of some pure entangled state in a larger Hilbert space. So it's not really clear if you should be assigning any significance to that. When I talk about preparing states by flipping coins, and given an outcome, I prepare some pure state, should you really be describing this whole thing as like some massively entangled state where whether I get result up or down, whether that's like entangled with the state that I'm going to prepare? It's not really clear how you should think about that. And I'll kind of come back to that at the end of the lecture.
So this purification procedure is not unique though?
It would not be unique, no. Do I even say that? I don't say that. No, but it's not unique. Yeah. And just some terminology, this thing would be called a purification of rho.
Is there any constraints on dimensionality over HA and HB?
It would have to be high enough. I think in general, the Hilbert space of we call it an ancillary space, so Hilbert space B, the dimension would have to be as high as the dimension of A in order to get it to work. Yeah.
I just thought that just using R would be...
Using what? R? Like an infinite dimensional space?
Yeah, like just one-dimensional space.
I don't think it would be enough.
Yeah. It would contradict the statement. Because then every density matrix would be equal to the state.
Yeah. No, it would have to, the dimension would have to be as high as the dimension of A. Yeah. Yeah, so I'm sorry I had to cover up what I just wrote, but I'll put the boards up again in a second. Okay, so that was preparations. So now let's move on to transformations. So just to remind you, the postulate for transformations was that realistic dynamical transformations are prescribed by CPTP maps, E rho. So CPTP stood for completely positive trace preserving. And this notion of complete positivity was to make sure that if we took a density matrix that was a positive operator, what we got out after applying the transformation was also a positive operator, so that the map would represent a physical operation. Okay, so we saw already that there was one way to implement a CPTP map, and that's by probabilistically applying unitary operations. So if I applied the unitary I with probability PI, then I could describe the map E rho as sum over pk, where p are the probabilities, and then just applying the unitaries as you would expect. And then I can write this in terms of these things we call the Krauss operators. Where the Krauss operators were just proportional to the unitaries. So as you might expect, there's a second way of doing this as well that doesn't rely on doing probabilistic mixtures. So the second way relies on, again, bringing in an ancillary system and applying a unitary operation on the extended Hilbert space. So just to get a picture of what's going on, I'm going to use the quantum circuit representation. It's a graphical representation of information changing as you apply quantum gates, but it's very intuitive. So, well, okay, let's say this is method 1. And then method 2, I would take my density operator rho A and introduce some pure ancilla system B. And then in a quantum circuit, we just have lines that go from left to right that represent time evolution. And then when we apply operations on the state, these are represented as boxes like this. So this just means applying the unitary UAB onto the tensor product of rho A and this outer product of phi. And then what I would get is some sort of entangled output state, but I could just ask the question, what's the reduced density matrix of this system A? I'll just call this rho prime. And I don't really care what's happening to this guy here. So it turns out that I can effectively take this whole thing here and describe that as a map acting just on rho of system A. So this would then be equal to just taking system A and sending it through a map, and then I get rho prime A is equal to rho A. And I will show you how that works. It's quite neat. Okay, so the thing that we need in order to show this is to just apply the ideal postulates to this system. So let's start with writing down the initial state. So the initial state will be rho A tensor phi B. And then I want to apply the unitary operator to both states. So I apply it from both sides. And keep in mind that this now is acting on both Hilbert spaces. And now I'm just interested in what's happening to system A, so I'm going to trace out rho B. And this should be the expression for rho A prime, what comes out the other side. So now what I can do is explicitly write out the trace. So I can have a sum over K over some basis for system B. Then UAB. And then I can use this trick because the operators on A and B commute. I can just move this guy over here and write satisfy B, then put row A in the middle. And then close the trace on the other side. And now hopefully you can see that this operator here, it acts on system A and B, but it's sandwiched between these Brazenkets for system B. So effectively what this will be is an operator acting just on system A. So I can call this AK, and this is just the Hermitian conjugate of that. And so effectively I get a map in terms of Krauss operators just on system A. Okay. So this is a slightly different, well, the form is the same, but this procedure here is actually more general than the procedure with probabilistic mixtures. So so both of these sets of operators satisfy this expression or this condition. Both methods satisfy that the sum over K, A dagger K, AK is equal to the identity. So that's the trace preserving condition. But only method 1 satisfies the condition one satisfies it's a very similar looking condition, but now the dagger is on the other side. So this condition here is something called unitality, and what that means is that it's a map that can that takes the identity to the identity. And so the consequence of that is that if you started off with something with a state that was maximally mixed, so it was at the center of the block sphere, proportional to the identity, there's no way to take a unital map to increase the purity of that state. So unital maps, the ones that are made with probabilistic mixtures, can only ever reduce the purity of your state, but they can never increase it. While these more general maps that you get by coupling to another system, they can actually increase the purity of your state as well. So in general, method 2 does not make unital maps, while the maps made by method 1 are constrained to be unital. Okay, and the same way that we did with the preparations, we can also go in the other direction. So there's a dilation theorem called the Steinspring dilation theorem. Which says that any CPTP map acting on an operator in Hilbert space A can can be expressed as the reduced action of a unitary acting on some extended Hilbert space. But this only holds under the condition that the initial ancilla system is uncorrelated with the system that you're interested in modeling. So it turns out that there's actually more general transformations you can have where if this system was initially correlated with this ancilla system, or like with the environment, then the effective description on that system wouldn't be a CPTP map. I don't think it's even a linear map. And actually, I'll take that back. But anyway, it's not a CPTP map, and it's a active area of research how you should model those. So if that is something you're interested in, I can give you a couple of papers on that. But everything we're saying here in terms of the postulates always assumes that the initial systems are uncorrelated. Okay, so yes?
By uncorrelated, you mean classically, right? Or?
Yeah, classically and
yeah,
quantumly.
so if they are not correlated, they are not entangled.
Yeah, can you have a state that is... So you can have states that are entangled but not classically correlated. And
Yeah.
So if it's a pure state, then the only correlation it has is entanglement, but it doesn't have any classical correlation. But you can also have states that are classically correlated and not entangled. So I would have to double check this, but I think this means uncorrelated in any way, so not classically correlated and not quantumly correlated. Yep.
Does sigma b have to represent a pure?
It doesn't have to be pure. And again, this is also not unique. So you can make many different maps that are effectively the same with different combinations of initial states and entangling unitaries. Okay, so we sort of saw some examples like this. So let's just have a look. So remember, I think it was end of last week, we were talking about spontaneous emission of a two-level atom inside a cavity. So there we saw that if we started off with an atom that was in the excited state and the cavity field was in the vacuum state, then as the state evolved due to coupling between the atom and the field, it evolved like this. So with some probability amplitude, an atom went into the ground state and emitted a photon. And so we could write an effective description for just the atom. And we could see that the atom evolves to an incoherent mixture of the ground and excited state. So in this particular example, you could see that as a function of time, it's going to, it's going to oscillate between being in the ground and excited state. And the reason you have this oscillation is because it's in the atom is in a cavity, so the photon never escapes and it can be reabsorbed by the atom. And so there we were able to solve things, in the larger dimensional Hilbert space. But let's say if you wanted to consider a more complicated example where you had the atom not inside a cavity, but inside, not constrained by anything, then to model the description of the atom and the field altogether, it would be a really complicated problem because you would have to couple to all of the modes of the radiation field, and it would be difficult to solve. But that's the point where we can use this idea of effective Krauss operators to model the evolution of the atom without having to treat all of the complicated degrees of freedom. So if the atom is not in cavity, then we can describe the evolution of the atom just in terms of two Krauss operators. Where the two Krauss operators in matrix form look like this. Where P is some parameter that is related to how long the interaction is on, or how strong the interaction is. And so you can see that these operators are now different. They're no longer operators that are proportional to unitaries. They've got some other strange form. And these type of operators, they can actually increase the purity. And it kind of makes sense. So if we go back to our block sphere picture, and I don't know, for whatever reason, the convention is to write these operators in a way that the ground state of the atom is at the top, not at the bottom. But so then if I start with some, mixed state in here, the effect of these operators is to, regardless of where the state is in the block sphere, it's always just going to decay to the ground state of the atom. And so the process of purification, the process of this decay can actually increase the length of the block vector and increase the purity. Because of course the ground state of the atom ultimately is a pure state. So regardless of where I start, I'm going to end up in the ground state. And so in this this Mathematica notebook that I showed you guys on a couple of days ago, you can download it from the wiki. And the last example that I didn't actually go through, but it has a model for this spontaneous emission of the atom, and you can play around with it and see how that behaves. Okay, and so now we can move on to the last postulate, which is the measurement postulate. And just to remind you, third postulate was that a realistic measurement procedure is represented by a POVM, which is this set of operators, EM. And the index M refers to the outcome of the measurement. And the probability of getting outcome M is given by this generalized Born rule. And the operators EM satisfy the condition that they sum to the identity, and they are non-negative operators. And we also saw that there was a state update rule. I'm just going to write the simplified version of it without the sum over I. So for a measurement, specifying the POVM was enough to predict the probabilities of the outcomes. But if we wanted to say something about how the state was updated after the measurement, we needed to go into a little bit more detail and specify how the measurement was done, which is encoded in the measurement operators. And so what that means is that there are different M's can represent different measurement procedures that would lead to the same statistics, but give you different post-measurement states. Okay, and we can do the same thing that we did for preparations and for transformations. We can describe POVM measurements in two different ways. The first way is to look at probabilistic mixtures of projective measurements. And then the second way is by introducing some ancilla system, evolving the entire system unitarily, and then just doing a projective measurement on the ancilla system. So I won't bother rewriting what we did in the first method, but okay, well, maybe I'll say just briefly. So method one was probabilistic application of projective measurements. And so then method two, we would take the system that we're interested in measuring and introduce some ancilla system. And then couple them using some entangling unitary, and then do a projective measurement on just the ancilla system. So we can go through the calculation just to convince ourselves that that's actually true. So, and doing that, we're just going to apply the realistic postulates. So we can start with what we want to do is start with writing down the initial state, evolve it using this entangling unitary, and then we'll get some state at the end. And then we can just apply the regular Born rule to this entire state, where we apply the projector on system B and do nothing to system A. So we can write the initial state as rho A tensor the density operator for rho B, and then evolve both things under this entangling unitary. So this now represents some big density operator at this point here. And then we just apply Born's rule. So the projector for just measuring system B is going to be the identity on system A times projector for system B. And then the Born rule says that we have to trace out over this whole thing. So that's going to give us the probability of getting outcome M. So now, I mean, this whole description is assuming that we know what's going on with system B, but we can write down an effective description for just system A by going through a similar procedure where, except it's slightly different. So we're not going to do the trace explicitly, but what we will do is write down the projector as just a rank 1 projector, and I'm going to drop the implicit identity. So we have the rank 1 projector on system B, and UAB, IB, and then I can use the cyclic property of the trace to just move this guy over to the other side. Or maybe I'll go the other way. Oh, let's go the other way. Okay, I'm going to use the cyclic property of the trace to get that and move that over to the other side. And again, so these unitaries act on system A and B, but they're sandwiched between bras and kets for system B. So now this is effectively an operator on system A, and I can identify that with my M dagger, and identify that with my M. And I can write this whole thing as just the trace of the measurement operator on row A, the POVM element where EM equals M dagger M, and M is this operator here. So I didn't do the most general case when, in the initial postulates, we had a sum over I as well. I think you can get that by putting in starting off with a, either it's by doing a non-rank 1 projective measurement, or it might be by putting in a mixed state here. I actually didn't have a chance to go through and check it explicitly. But if you want to, I mean, there should be something you can check for yourself if you're interested. But there would be a way to get the generalized version of the POVM implementation. Okay, and of course we can go in the other direction, the same way that we did for the transformations and the preparations. So there's another dilation theorem called the Neumark's dilation theorem, or Neumark. which says that for any POVM and any state row A acting on Hilbert space A, there exists projective measurement PM on system AB on Hilbert space AB and a state IB such that so the way that I've written it here is I have this projective measurement on system A and B, but that would just be the description of a measurement described by this unitary operation times a projector on just the subsystem. So you can always decompose a projective measurement on two systems into a unitary operation on both systems and a measurement on one system. And I don't want to go through and write that out, but it's in the notes if you want to take a look after the lecture. Okay, so the same way that we saw with transformations, that by coupling to another system, you could do more general non-unital maps. With POVMs, you can do more general, interesting POVM operations by coupling to another system. So I want to give you a few examples of POVMs that we can do that are actually useful in practice for contrived tasks, but still you can show that they allow you to do certain things that you wouldn't be able to do just with projective measurements. Okay, so let's consider one example. So imagine that I have a friend who is in the habit of preparing states. And this friend tells me that they're going to, with 50% probability, prepare this state, and with 50% probability, prepare that state. And my task is to make a measurement on that state and try and say with as much certainty as possible which state was prepared. So this is a task about distinguishing this state and that state. And I mean, if the two states were 0 and 1, then that would be easy because they're orthogonal states, so I can just do a projective measurement. But here, these states are not orthogonal, so there's no projective measurement that will be able to distinguish between these two with certainty. But what I can do is something called a Hellstrom measurement, which turns out to be the optimal measurement for discriminating between these two states. And that measurement consists of two projectors, so one of them here and one of them there. So I will just call them E plus and E0. And these projectors are the best that we can do. So the problem with doing this, so you can see, I guess, visually that there's more overlap between the state 0 and the projector 0, and than there is between the state plus and the projector 0. So if you get the projector, if you get the outcome 0 when you make this measurement, then it's more likely that the state that was prepared was this state. And if you get the outcome plus, then it's more likely that the state that was prepared was that one, but you can't say with certainty. So there's always going to be some chance that you're wrong when you go through this discrimination procedure. Okay, and you can check this for yourself by going through and computing the relative probabilities of, given preparation 0, what's the probability of getting outcome 0, given preparation 0, what's the probability of getting outcome plus, and so on, and looking at the 4 combinations. But the probability of all 4 combinations is non-zero. Okay, so then that's the best that you can do, and it doesn't work with certainty, but you can construct a different measurement using a POVM that will, it won't always work, but when it gives you an answer, you know with certainty that you have the right answer. So the 3 POVMs, okay, yep. So let's try this POVM. And the 3 POVM elements for this are E1 is proportional to the projector onto the state 1. E minus is proportional to the projector onto the state minus. And because we need our projectors to sum to the identity, we need to introduce a third projector, third POVM element, which I'm going to call E fail, which is the identity minus E1 minus E minus. So just to give you a sense of what's going on here, I'm going to kind of draw these on the block sphere. So E1 would be somewhere here. E plus would be somewhere here. E1 would be somewhere here. And then because you want them all to sum to the identity, then E fail would be somewhere here. So now we can see that the probability, yeah. Yes. Good. Yep. So, so the probability of getting the outcome 1, given that the state was 0, is 0, and the probability of getting outcome minus, given that the state was plus, is also 0. So now if we do this 3 outcome measurement and we get outcome 1, then we can guarantee that the state was prepared in the plus state. And if we get outcome negative, then we can guarantee that the state was prepared in the 0 state. So now we can, given a certain outcome, we can tell with certainty which state it was. But unfortunately, sometimes we're going to get this third outcome, E fail, and then we just say, well, I don't know, like flip a coin or something. So it doesn't work with certainty 100% of the time, but it works with certainty some of the time, as opposed to the other situation where it never works with certainty.
Aggie, why don't you just choose E1 equals projector onto 1 and E minus equals projector onto minus, and then E fail is just 0?
Because then they wouldn't sum to the identity. And then they wouldn't make a POVM. Okay, so then the second example of where generalized measurement can be useful is in the context of making a weak measurement, which is a little bit related to your homework as well. So this task of discriminating between non-orthogonal states and the idea of weak measurement are both sort of related to your homework, but not exactly the way that it's done here. Okay, so we're familiar with the idea of projective measurements. When you make a projective measurement, you get the most information that you can about a particular state that you can get from a single measurement, but you also disturb it maximally because you project it into a state that corresponds to the outcome that you got. So we can do a slightly different type of measurement, which I will do by applying entangling unitary to the system I'm interested in and the ancilla. So the unitary that I want to apply is something that, given system A being in the 0 state, I'm going to do nothing. And if system A is in the 1 state, I'm going to apply a rotation about the x-axis by some angle. So I can decompose that rotation in terms of Pauli operators. Okay, and so let's say I want to make a measurement on an initial state that was prepared in some coherent superposition of 0 and 1. So I could just make a projective measurement on this state and get all the information that I want, but then I'm going to disturb it, which, for example, for a quantum control task, like in your homework, it can be a bad thing to disturb the system because you want to disturb the state, because you want to preserve some information about it. So what we can do is introduce some ancilla system. So let's write our state A. And then I'll prepare my ancilla in state B. And then I apply UAB to that system. And let me just rewrite it. Okay, so I haven't yet applied the unitary, but I just expanded everything out. And then if I do apply the unitary, then given system A being in the 0 state, it won't do anything. So I get 0, A, 0, A, 0B. And then if I'm in the 1 state, I apply this operation. So I get so it might not seem immediately useful yet, but let's consider a couple of limiting cases. So if chi was equal to pi on 2, then after applying this operation, the state would be the combined state of the two systems. And if chi was equal to 0, then the combined state would be okay, so we've applied some unitary, and now the next thing that we want to do, according to that diagram, is to do a projective measurement on system B. So you can see in this case, if I measure system B, I will be effectively doing an indirect measurement on system A. So this is kind of similar to what happens in Stern-Gerlach, where rather than where the two systems are the two different properties of the spin particle, where you first start with the spin degree of this. The particle can be in some superposition of spin degrees of freedom, but then after going through some magnetic field, it couples to the position degree of freedom, and then the beams split up like this. And then you measure the position of the particle, which then effectively gives you information about the spin of the particle. So this is kind of what's going on here. By measuring B, we effectively do a projective measurement on A. But in the other extreme, if chi equals 0, then what comes out is totally uncoupled. And so a measurement of B is going to give me no information about A, but it won't disturb A at all. It'll leave it untouched. And so then by changing chi, which is some parameter on your entangling unitary, you can actually tune the trade-off between the amount of information you gain about the system and the amount that you disturb the system. And for certain tasks, a parameter that's somewhere between 0 and pi on 2 might be useful. And so that's something that you will see in your homework, that you can implement this quantum control scheme optimally by picking some parameter between doing a projective measurement and no measurement at all. So the concept is going to be similar to your homework, but the operations I picked are probably different. So don't copy it directly. Yeah. Okay, so we've kind of, over the last 4 days, we covered a lot of stuff. We looked at the 3 different postulates in 3 different ways. And what I wanted to do was to construct kind of a table, like an infographic, that ties everything together. And I was going to do it at the end of the class today, and we definitely have time to do it, but I actually think that it would be better if you have some time to process the stuff that we covered today, and then we can just do it at the beginning of tomorrow's class. I think it'll be better to tie everything together then. So we're going to finish early today. Nice. But the final thing that I wanted to say was, so this idea of taking either some sort of density operator or some sort of CPT map or some sort of POVM, and then dilating it by introducing some ancillary system and then performing operations on the extended Hilbert space. So the terminology for that is something coined by John Smolin, which is called the going into the church of the higher dimensional Hilbert space. And so the reason it's interesting to consider that, because so it's a mathematical operation that we're doing, but perhaps you might want to assign some physical significance to that. And whether you should do that or not is something that's up for debate. There's no consensus in the community about whether you should think that there's something physical about the fact that you can always dilate your operations into ideal operations on a larger Hilbert space. So some people are for this and some people are against it. So one person, Matt Leifer, who is going to be doing the Quantum Foundations course in January, I think he is a person that is against the church of the larger Hilbert space. And so he actually has on his website a set of commandments for the church of the smaller Hilbert space. It's just a joke, but it's a joke that now you will be able to understand because you've seen all the material. So I'm just going to hand it out to you guys, and yeah, you can laugh. But yeah, we'll finish early today, and then at the beginning of tomorrow's lecture, I will just tie everything together that we've done in the last 4 days, and I'll talk about teleportation. Oh, and then I think we're going to have a Q&A. Is that right, Meta? For like the second half of tomorrow's lecture? Yeah? Okay, just for my part. Okay, so yeah, you'll be there for the tutorial. Okay, yeah, so we'll pretty much just have like a half lecture, and then we can move over to the tutorial room, and hopefully you guys will have a bunch of questions that we can just chit chat and I can answer them away from the cameras.